Okie dokie. So, hello everybody, and welcome to this little, I suppose, a mini masterclass. We're going to talk about lasers and IPLs and a little bit of physics and a little bit of treatments and stuff like that. So, let's crack on. Click, click. So the goal of all this is quite simple. What I try to teach people and instill within them is to laser with confidence, because what I found through the years is that so many people out there buy machines, buy devices, and then they don't really know how to use them properly, and they end up guessing and kind of fudging and they're always just a little bit scared and then they wonder why they're not getting good results. And it's quite simply because if you're not confident in what you're doing and the technology you're using, you'll never get good results unless you're extremely lucky, which just unfortunately doesn't happen in this world. So let's start off with a little bit of physics and some of the kind of basic stuff. So we talk about light and heat because we're firing in light energy into the skin, and inevitably that generates some heat energy, and then all the magic happens. So to understand how this works properly, there are a few terms that you really should understand. Fluence is one of the most important things. Wavelength, obviously, pulse width or pulse duration, and then other things like absorption, scattering, and backscattering. If you understand all these kind of basic terms and the principles behind them, then you will have a much greater understanding of what's actually happening in tissues. All right, so we're going to go through all that this morning. As my wonderful wife said to me one day, it's not rocket science, it's laser science, which I must get printed onto a t-shirt one of these days. And I thought, yeah, I'm gonna steal that because that's quite cool. That's a good expression. So light, let's start off with light. All light is formed by essentially photons striking atoms. And in the atom, you've got your nucleus and you've got an electron, and the electron will absorb the energy of that photon and it jumps into a higher orbit, as you can see here. And then, but the thing is, though, they don't like sitting in that higher orbit for long. It's a very, very short duration. So they drop back down into their standard orbit, or what we call the ground state orbit. And as they drop back down, they emit a new photon with exactly the same energy that the old photon had. So this is the principle behind all light being generated. Okay, so this happens like in stars, it happens in your light bulbs above your heads and your mobile phones. This something's happening where the electrons are being excited, and when they de-excite, out pops a new photon. Now the thing is that the photon energy, this little guy here, the amount of energy each individual photon contains depends on these orbits. So this orbit, the ground state orbit, this one down here where the electron's sitting there quite happily, this has a certain amount of energy. The next orbit up has a little bit more energy, and the next orbit up will have more, and so on and so forth. And so the photon energy must equal the difference between these two orbits. It can't be like out here somewhere or in here or maybe in there. It's got to be precisely that difference. And that's why this is what drives absorption. If that photon meets this electron and they have a little exchange, a little discussion, and the electron says to the photon, how much energy do you have? And the photon might say, I've got 2.2 nanojoules of energy. And the electron says, oh, but this orbit up there, the next orbit is 2.5 nanojoules away. I can't reach it with your energy. So you on you go. Bye-bye, cheerio. And it sends the photon away. Because that energy is not enough for the electron to jump up to the next orbit. Or it might be too much. It might overjump, might overskip and go to some limbo land between orbits. Can't do that. It was a Danish scientist called Niels Bohr who realized this about 120 years ago or something like that. And he realized that all these orbits of electrons are discrete. There's no space in between them that they can exist. And therefore, the photon energy has to match the difference in the orbit's energy. Otherwise, it cannot be absorbed, in which case it goes off in its way. It's essentially it's scattered. Okay. The old Bohr model Niels Bohr came up with kind of looks a bit like this. It's a bit like you can think of it a little bit like the solar system, where you've got the central nucleus here, where the sun might be. The nucleus is composed of protons and neutrons, and then swimming around out here in the different orbits are the electrons. So that was the old model that Niels Bohr came up with, but a chap called Schrödinger, a German scientist, realized some years later it's not quite like that at all. It's a bit more like this, where we don't have discrete electrons kind of orbiting like planets. It's much more like this idea of electron clouds, but you still have the, oh, here comes Vivi. You still have the discrete orbital um, spacings. So even though you've got this kind of cloud where we don't really know where the electrons are, it's almost kind of like they're sort of smooshed out. Smush, I think, is a Swedish word. I think I just made it up. I don't know. So the electrons are kind of smooshed out in this orbit, but the orbits are still discrete. So the same rules still apply in terms of generating new photons and such. But this model now, the Schrodinger model, is generally accepted amongst the world's physicists as this is more representative of atoms and such likes. So that is when we view photons as a little discrete, almost like a particle. Einstein called them quanta. He came up with this notion a long time ago, but now these days we call them photons. But that's when we look at the energy packets, you could say, a little kind of almost like a little particle of light. But light is also viewed as waves, and because they're known as electromagnetic waves, so you have a magnetic field that oscillates back and forth, and perpendicular to that you have an electric field which oscillates back and forth, and then both fields move through space in the third perpendicular direction. So all electromagnetic radiation looks something like this, and you can change the wavelength between the peaks and the troughs. You can change the amplitude, which changes the amount of energy and what have you. And so this is how light is viewed when we look at it as a wave. So this is the bizarre thing about light. Light is a strange substance, because it depends on the detector, how you view it. You can see it either as a particle or particles, or you can see it as a wave, and it's your detector which determines that. So the human eye, our eyes, pick up these things as particles, individual photons. But if you use, whoops, if you use other kinds of technology. I can't think of one at the minute, but there's all kinds of technology which would look at light, and they would observe it as waves. This is why we get refraction and diffraction and all this kind of thing. But other technologies, like your camera phone, for example, in your cameras, they pick up light as particles. So this is one of the weird, bizarre things about light that's still not fully understood. We call it the wave-particle duality because it can be seen as both types of manifestations. Mostly when we're talking about tissue interactions with lasers and IPLs, we tend to talk about light as photons, okay? But if we look at the spectrum, this is the visible spectrum that most human beings can see, typically between 400 and 700 nanometers. So the 400 nanometer light is typically blue, 700 is red. If you extend beyond the 400, you go into the ultraviolet range, which is invisible to us, but quite dangerous for the skin and the eyes, because the photons can damage the DNA and the RNA as well, in fact. And if you go beyond the 700 into the infrared region, again, it's invisible to human beings. Some animals can see this, so nocturnal animals in particular. Even cats and dogs can see into the infrared, which human beings cannot, which is why they can see things at night. And we can't see infrared, but we can feel near infrared as heat. So when you walk out on a sunny day, uh, unlike today here in Scotland, but in Finland today, I understand it's sunny. If you walk outside and you feel the heat from the sun, what you're feeling is the infrared energy, not the visible energy. We can't feel much heat at all in visible light. We can see it, but we can't feel it. But when you feel the heat from the sun, it's the infrared is what you're feeling, because it's infrared is going into your skin and it's exciting the water molecules, and that's the heat that you're feeling, right? So that's how you know. You can't feel ultraviolet either, but it stimulates your melanocytes to generate lots of melanosomes to protect your dermal skin layers. So most skin lasers typically operate somewhere in this kind of region, from kind of the far end of the blue through all the visible and into the near infrared. And then some lasers, like CO2 laser, for example, it goes quite far out into the infrared at 10,600 nanometers. So typically that's what the range of our lasers that we use. Although you can get some ultraviolet. So the excimer laser, for example, it's an ultraviolet. It's down at 193 nanometers, so it produces an invisible beam. But it's good for things like psoriasis, for example, and it's also used in ophthalmology as well. But most skin lasers don't go down that far into the blue spectrum. So wavelength, what is wavelength? Well, wavelength is just the length of the wave. Hey, nice and simple. We physicists like to keep things nice and simple, as you know. So the wavelength of this particular wave is the distance between that peak and that peak, or the distance between that trough and that trough. It doesn't really matter where you measure it, as long as it's consistent. So, and most people, you view the wavelength as the color. That's what color essentially means. So if you say that apple is red, I, as a physicist, would say that apple is 725 nanometers. There you go. We're just a little bit more precise than most people. But interestingly, when it comes to skin and tissue interactions, the wavelength is not really the important thing. It's the corresponding absorption coefficient. And the absorption coefficient tells us how strongly that particular target in the skin absorbs the light energy. So if you have a target, let's say tissue water, okay, water, we know water doesn't absorb strongly in the visible spectrum. So let's say you fire some green light at, say, 530 nanometers, and you fire it into the skin, then we know that the absorption coefficient for water at that wavelength is very, very low. So the water is just not going to absorb any energy at all. And that's why visible light doesn't really heat up the skin, because there's not much of an absorption there at all. But if you go into the infrared part of the spectrum, well, then the absorption coefficient starts to grow. Hang on, here's Mila. It starts to grow, and you get more of the energy being absorbed by the target, particularly tissue water in the skin, and then you start to get the effects of that, which is usually heat. Okay, so the absorption coefficient is the thing that we really are interested in. The wavelength is kind of, it's obviously it's tied, but what we want to do is we want to match the wavelength to the highest absorption coefficient in whatever the target is, whether that's melanin or hemoglobin or tissue water or tattoos or whatever. So that's what we're trying to do with our lasers and our IPLs. Okay, you maximize that absorption. Each individual photon has got a tiny, tiny, tiny amount of energy. I mean, we're talking like
Eikö
itsy
sulla pihalla?
bitsy, teeny weeny, as we say in English.
Haluan viedä, että aamulla
Mila, can you turn your microphone off, please?
saat liikkumatta ja katsoa vähän silleen, että saatana kosketko.
No idea what you're saying.
Ja mennään pihalle pistää.
Mila, hello.
Oh.
Hello, can
Sorry.
you turn your microphone? There we go. Thank you. So if one photon has got a tiny amount of energy, then 1 joule, which is 1 joule's quite a lot of energy, is equivalent to that many photons, 5 with 18 zeros. All right, so that shows you how little energy each individual photon has. It's 1 over that 5 Brazilian whatever. I don't know what the English word is for that many photons. In physics, we don't tend to use that kind of language. We talk about 5 times 10 to the 18 photons. That makes a lot more sense to me. So there you go. You can see right away that a single joule of energy has got so many photons, and you fire that 1 joule into the skin, then all those photons have got to go somewhere. Either they're absorbed in the skin, or they're scattered out, or they penetrate out into the subcutis or wherever. So it's a lot of photons that we're dealing with. If you fire these photons into a large area like this, then you're going to get quite a low spread, it's going to be spread out over a larger area. So it's quite a low concentration. If you shrink that spot into a much smaller area like this, and it's the same number of photons, but in that area, then obviously it's a much greater concentration. So you can see that having a big spot size, the concentration is low, and therefore the effect on the tissue is relatively low too. But the same number of photons, you can imagine all these guys going into that small area instead of that, then suddenly you're going to have much more of an effect. Okay, so the concentration is really quite critical. So I got a wee message here from somebody. Antis Antixi. Antixi. What's that? Hello? um, And this is what fluence means, right? Fluence is just basically the energy you're firing into the skin divided by the spot size area. We measure it in joules per square centimeter, and all it really is essentially the concentration of energy. All right. So if you set your machine up and you plug in, say, 5 joules on the screen, and you have a certain spot size, say 5 millimeter square or whatever, then that gives you a certain fluence or concentration on the skin surface. Okay, if you double the energy, then you double the fluence. If you half the spot size area, then you double the fluence again. Okay, so you can change either the total amount of energy, which is the number of photons that you're firing in, or you can change the spot size area, the diameter, and both of those will change your concentration of the fluence, right? And the important thing is that the fluence is what drives everything. The fluence is what generates the temperature rise. If you have a cooker, I don't know if you have gas cookers in Finland these days, I'm not sure. But if you have the old style, we used to call it gas Mark 6, that was the hottest that your cooker could generate, then that gas Mark 6 will fire more gas into the ring and therefore gives you much greater temperatures than gas Mark 1. And it's exactly the same with fluids. A high energy fired into the skin gives you much more fluids than a low energy. So choosing the correct fluence is absolutely critical because it's the fluence that drives the whole process in the skin. If you have too much fluence, you're going to overcook and cause lots of unwanted damage, potentially leading to scarring. If the fluence is too low, then you're not going to get very far because you're just going to heat up your target just a little bit, but not enough to do the job. So you got to get the right concentration, the right balance in there, so that you're creating enough damage in the tissue target, but not creating damage all around it too. That's the tricky part, and that's what we're going to talk about today in this session and the next session. The way this tends to work in the skin, if we look at the depth of skin's going that direction, not down the way. It's a bit weird, but there you go. So there we have this is the skin surface. That's the epidermis. Then you've got the basal layer, which is very thin, and then that's the dermis. And if you fire the light in from the left-hand side here, and you fire it into the skin, it generally goes something like this. It's kind of like an exponential drop. Now, it's not exactly exponential because it depends on what is in the skin, whether there's a lot of water or blood or tattoo pigment or whatever. So this is a sort of an idealized representation. So there's always going to be more energy near the surface or just below the surface compared to deep in the dermis. And this is the same for pretty much all wavelengths that we use. All right. The only real difference, I suppose, is CO2, where the energy is absorbed very close to the surface, because as soon as CO2 hits water, the water absorbs all the energy, so it really doesn't penetrate deep into the skin at all. But pretty much most other machines that we use in IPLs, this is kind of what it does, and this is why it's difficult sometimes to treat deep targets. If you get something that's deep down here in the skin, then by the time the energy has reached that depth, there's not much energy left. It's all been dissipated and absorbed up here in the superficial layers, but deep down here. So what that means then is that if you're trying to target something down there, which could be a blood vessel, for example, or a hair follicle, then you're going to have to fire in more energy, more fluence at the surface just to get sufficient energy down to at that depth. But the problem is if you fire in more energy or more fluence at the surface, you're going to get much more absorption in the superficial layers, especially in the basal layer where the melanin lives, and potentially you could be damaging that. So we have to balance that damage near the surface so we get enough damage down here but without causing excess damage up here. And I'll show you how we do that later on. Okay. Pulse width is also known as pulse duration or pulse length. Just depends who you talk to. Engineers like to call it pulse length, and physicists call it pulse duration or pulse width. So it doesn't matter. They're all the same thing. But what basically this means is this is the time over which the light energy is being delivered into your target, into the skin. And so it can be milliseconds, nanoseconds, picoseconds, or minutes, or hours, or days even. If you boil an egg, and you're boiling it for 5 minutes, then your pulse width is 5 minutes because you're delivering the energy into that egg for 5 minutes. That's what it means. Okay, but in terms of light energy, we have a fairly specific description. We use this technology here, full width, half maximum. So you take one of the waves, you say, okay, there's the peak of the wave, so this is halfway down, and then you measure the distance between the start and the end of the wave at that point. So this is the full width, half maximum. We call that the pulse width because that will not be the same as if you measure it down here or you measure up there. So this is the actual technical definition. Who cares? Big deal. That's that for us. That's not really so important. But the pulse width can determine the maximum temperature in your target because if you have a short pulse, you fire a short pulse at say 2 or 3 milliseconds into your target, then there's no time for any heat energy to escape during the pulse. So the energy is being kind of stacked up in the pulse because it's just not getting enough time to escape. And that can then lead to a very hot target during the pulse. Obviously, after the pulse, the heat can escape. But during the pulse, hang on, there's Millet again. During the pulse, there's no time for it to escape, so it gets hot. So conversely, if you fire the same energy, exact same energy in the same spot size, same fluence, same everything, except you use a longer pulse now, then during the pulse, there's more time for the energy to escape into the surrounding tissue, and therefore you get a cooler target. It doesn't get as hot as a short pulsed, right? So basically, if you've got a machine, let's say you've got your laser or your IPL, and you set it to output, let's say for talking sake, 10 joules per square centimeter. If you then set the pulse to 1 millisecond and you fire it at a target, it will generate quite a hot target. If you fire the same pulse except over 10 milliseconds, so it's taken 10 times longer to deliver the same energy, same fluence, then it will be much cooler because during that 10 milliseconds, a lot of the heat will have escaped while the energy is still being absorbed. Okay, so the pulse width is very important in certain situations. I'll come on to that in a bit more detail in the next session this afternoon because it's important for hair removal in particular. Okay, so when light hits a target, let's talk about absorption. What happens? So if you have a red target light, so imagine this is a red apple, all right? And you're firing red, blue, and green light at the apple. Well, what happens is that the little atoms and the molecules in the skin surface of the apple, they like the green and they like the blue, so they absorb that energy, but they don't like the red. So the red light gets reflected. That's why a red apple appears red, because the atoms and the molecules in that red skin don't like red. That's why it appears red. So this is kind of counterintuitive. Because if somebody gives you a red apple and says, why is this apple red? You might think it's red because it likes red light. No, it's red because it doesn't like red light. This is the kind of the weird thing, right? Likewise, if someone gives you a green apple, then the reason it's green is because it likes the blue and the red, but it doesn't like green light. So it reflects the green light back out. If someone gives you a blue apple, then that's very strange. I'm not quite sure where you might get a blue apple from, but you might have a blue apple or a blue something, maybe, I don't know, plum or something, whatever. And it's the same principle. The blue, the atoms in the blue skin absorb the red and the green light quite happily, but reflects off the blue light, which is why it appears blue to our eyes. So black absorbs all the colors. That's why it's black, because it's not reflecting very much color at all. And white is the opposite. It reflects all the colors. Okay, so black and white are not actually colors. Blue, green, and yellow, and orange, and pink, and whatever, they're all colors, but black and white are not colors. Black is essentially a lack of color, and white is essentially a reflection of all the light, so it's all the colors, you could say. But there's no, you can't sit down and write, yes, black is 216 nanometers. Doesn't work, okay, because it's not. So what we're trying to do when you're firing your light energy into the skin, you're trying to match rather the wavelength that you're firing with the absorption coefficient as closely as possible, so you can achieve the maximum absorption of light. Let's say, for example, let's say in the red case, you're targeting blood. Okay, so hemoglobin is red. If you look at blood, typically tends to be red. So if you fire red light at red blood, well, you're not going to get much absorption at all, because the reason the blood is red is because it doesn't like red light. It reflects it straight back out again. So firing red light at red blood is kind of pointless. You're not going to get very far. We know from experiment that the best colors to fire at red blood are actually yellow and green light, which is why we use pulsed dye lasers and IPLs with certain filters, because that will allow through the yellow and the green wavelengths, and they will be strongly absorbed by blood, whereas red light just gets reflected straight off. All right, so that's how we do it. You match the wavelength with the absorption coefficient of your target to maximize the amount of absorption, and then you get the maximum possible temperature rise in that target. So where does light go when you fire light into the skin? So if you remember, one joule of light generates a Brazilian photons. I call them Brazilians because I can't think of the right word for it. I don't know the right word for it, so I'll call it a Brazilian. Apologies to all Brazilians out there. I don't know who there are in Finland. So you fire in all these little photons into the skin, and there's only four things that can happen. It'll go into the skin, and it could be absorbed maybe somewhere in the basal layer in the epidermal junction, with the dermis. So it doesn't go very far at all, but when it gets absorbed in the melanin there, it will generate a little bit of heat. Each individual photon will generate a tiny, tiny, tiny amount of heat. If a lot of photons are absorbed in the basal layer, then you get a lot of heat being generated. Or if it goes through the basal layer, it misses that, bounces around, scatters in the dermis until eventually it's absorbed by something in the dermis. That could be hemoglobin, it could be water, it could be melanin down there, it could be keratin, it could be anything at all down there. If it doesn't do that, it keeps bouncing around or scattering, as you say, and does this little trip. Then eventually it can go into the subcutis, and it could be absorbed by some adipose cells, or again, it could be absorbed by water down there. It just depends. And we call this transmitted because it's been transmitted all the way through the epidermis and the dermis, and it's now in the fat tissue. Now, the thing is, though, it doesn't necessarily stop there, because it could be scattered about in the fatty tissue, and it might come back out into the dermis and be absorbed in there. Or it might, in fact, just do like this case here. It bounces about and gets scattered out back into the air. Hang on, I'll get a couple more people joining us. Okie dokie. I think it's two more ladies. Hello, ladies. How y'all? We're just talking about photons and where they all go in the skin. Hang on, let me just kill this. So essentially, there's just a few things can happen with photons in the skin. Either it'll be absorbed by something, water, melanin, hemoglobin, keratin, whatever, or most likely it'll be scattered. Pretty much all light will be scattered, which just means it's bouncing about all over the place before being absorbed or back scattered out. If it's back scattered, it leaves the skin altogether and goes back into the local environment, and most likely it will not go back into the skin. Highly unlikely. And we can lose a lot of energy through backscattering. Or it may be transmitted into deeper layers, into the subcutis, or even potentially into muscle tissue if it gets through the subcutis. Now, interestingly, I'm doing some work on this at the moment on that computer over there. looking at where all the light goes. And I've discovered just recently that quite a lot of the light which goes into the fatty tissue down here actually does get backscattered into the dermis, much more than we previously thought. So a lot of the original modeling is wrong because people assumed that once the light goes into the fatty tissue, that was it lost. We couldn't use it anymore. Turns out that's wrong. We can actually get something like 30% of it back, and that is significant. So I'm doing some more work on this at the moment. I'm going to try and publish this some point this year because that has a significant effect, particularly on hair removal treatments. Because a lot of hair, I only discovered last week that some hair follicles can be as deep as 3 millimeters in the fatty tissue, which is a lot deeper than I realized. I thought it was quite superficial, but it is deeper. So we're still doing work in these things, trying to figure out where all this light goes and what it actually ends up doing when it gets there. Right? Quite a journey. So basically, it comes down to two things: scattering, where the photons are bouncing off all the atoms and molecules, and this can happen many times, like millions of times before finally that photon is absorbed by something. Okay, so when you fire light into the skin, this is happening. In fact, it's happening right now. As you're sitting there in Finland and I'm sitting here in Scotland, it's happening right now. All the light that's bouncing into your or going into your skin is scattering and bouncing all over the place, and then either it's being absorbed by something in there or it's emerging back out into the atmosphere. Now, the reason you can see, if you look at your skin, you can't see it there, but if you look in at your skin and you can see, for example, blue blood vessels, or you might see the red blood vessels, all that is backscattered light. That's light that's into the skin, bounce about, hit the blood vessels or the hemoglobin in the blood or the tissue water, whatever, and come back out, and we can see it. And that is backscattered light. So all the stuff you can see where you can look in essentially into the skin, that's what you're seeing. If you look at your wall and you see the paint on the wall, there's virtually no backscattering happening there at all. That's why you can't really see much beyond the surface of the paint, because paint just doesn't backscatter. Well, most paint, probably some paints do, but most paint don't. So that's the difference between something that's kind of sort of translucent, which the skin is. You can see a lot of backscattering, and something which is not translucent, like your paint on the wall, and you don't really see much beyond the surface. Okay, so scattering is highly important. It's extremely important, and absorption is also important. Absorption is what we're trying to achieve. You're trying to get absorption in your target, but unfortunately, we have to go through this whole scattering phase before absorption happens. All right. Hope this all makes sense. Everybody say, yeah, yeah, I can hear you. So high absorption or a high absorption coefficient means that a lot of energy will be absorbed, and that will then result in high temperatures, hopefully. So by matching the wavelength with the absorption coefficient, we will get the highest temperatures. This is why we have to do all these experiments in laboratories where you take things like melanin and you separate it out from everything, and then you fire light through it and you measure what comes through the other side. That tells light of different wavelengths. That tells us then, okay, we should use this wavelength to target that, or that wavelength to target this. That's the whole idea behind the selectivity. You've probably heard of selective photothermolysis. Well, this is what part of the selection process is, matching the wavelength correctly with the target. In physics, we use this little symbol mu A, mu from the Greek language, A meaning absorption. We have mu S for scattering, mu T for transmission. And mu A is essentially the color of the target. That to human beings as people, when you look at something and you say that's blue, that's pink, that's red, that's orange, essentially what you're describing is the absorption coefficient. You didn't know it, but that's what you've been doing all these years. There you go. So next time you go to IKEA, you say to them, I want some paint for my kitchen, and I want it to have the absorption coefficient of 46.7 inverse nanometers, and they'll go, get out and don't come back here. That was my kind of nearly Swedish accent there. I can do a Swedish accent because I did a lot of work with some friends in Gothenburg 20 odd years ago, and I tried to learn Swedish, and it was bloody terrible. My Swedish is, how do you say scheisse in Swedish? Must be something similar. So anyway, let's look at, oh, hang on, we got somebody joining us. We look at, here we go, the absorption coefficient for melanin. So this is what it looks like at very low wavelengths here, down at 350 nanometers. So that's ultraviolet. The absorption coefficient is very, very high, because melanin is essentially, its job is to absorb ultraviolet light. So the idea is that ultraviolet hits your skin, the melanin in the melanocytes or the melanosomes absorbs that UV to stop it from penetrating into the dermis, because we don't want ultraviolet light in the dermis. Ultraviolet photons have very high energies, and that energy is extremely disruptive in DNA and RNA. It'll tear apart the proteins and cause mutations. That's why we get skin cancer from too much ultraviolet exposure. So the melanin absorption down at this part of the spectrum is very high to stop that ultraviolet light getting into the dermis. But as you go up through the wavelengths, so we're at 400 is visible, so all the stuff is visible here, up to about 700, which is the end of the top end of the visible spectrum, then you can see that the absorption by melanin drops significantly, because by the time you get to 700 nanometers, the photon energy is much lower. It's, well, in actual fact, at 700 is precisely half the energy of a photon at 350 nanometers. And such a low energy at 700 nanometers is not dangerous at all. Right? It'll not do any damage to your, well, the probability of doing damage is extremely low. It could still do it, but it's very, very low. And then once you go into you cross into the near infrared, which is invisible to us, and you're up at this part of the spectrum, then the absorption coefficient of melanin is very low. Right? As you can see, it's way down here somewhere. So it's not dangerous at all. But all the lasers we use, alexandrite, diode, neodymium YAG, they all generate wavelengths out here in the near infrared. And you might think, well, why do they do that? That's what, the absorption is so low. Why would you use those wavelengths? Well, there's two answers for that. First of all, the absorption is very low, yes, but it means that we're not anywhere near this kind of damaging range of wavelengths down here. So we're much, much, much less likely to cause any serious mutagenic damage, for example, in cells. So the chances of generating any kind of cancer is extremely low with these wavelengths. And secondly, these wavelengths can penetrate quite deeply into the skin, down to the subcutis, whereas these wavelengths can't. They just can't get down there. So if you want to try and get deep hair follicles and try to heat it up, firing these wavelengths is a waste of time. They just won't do it. This wavelength range between 500 and 600 is strongly absorbed by hemoglobin. So all the blood vessels in the superficial, the capillaries and what have you, will absorb a lot of that energy. So that won't be absorbed by the melanin in the hair follicles either. So it's kind of pointless firing these wavelengths at hair. It's just not going to get down there. It'll be absorbed by either superficial melanin in the basal layer or by the hemoglobin in the blood. So that's why we tend to use all these wavelengths for hair removal. We use these wavelengths for blood vessels, and we do actually use some of these wavelengths if you want to treat superficial pigmentation in the epidermis and the basal layer. Then actually these wavelengths are pretty good, because they'll be strongly absorbed in the melanin and they don't penetrate much deeper than the epidermis anyway. So they actually are quite useful for that treatment. Okay, so by selecting the right wavelengths, you determine which targets will absorb that energy at which depths. And that's very important, because there's no point firing low wavelength light like this stuff here to try and kill hair, because it just can't get down there to the hair follicle. It's pointless. All right. So let's look at the skin color and your Fitzpatrick scale. Now, Fitzpatrick was an American dermatologist who lived in San Diego back in the 70s, and most of his patients were people presenting with some kind of skin cancer, basal cell or squamous cell, or sometimes melanomas. And he developed this scale from 1 to 6 as a way to classify his patients essentially into probability bins, you could say. So a Fitzpatrick 1 was somebody whose melanin concentration was extremely low, 1 to 2%. So this is Scottish people, Finnish people, Swedish, all the Nordic races, Danish, Norwegian, everybody lives up near the North Pole. We all have very, very low skin color concentration because we don't get so much UV up here. So our skins have evolved over time to not generate so much melanin because there's so little ultraviolet. So that very low concentration means that we are highly susceptible to ultraviolet radiation. So if we do go to a nice, hot, sunny country like Italy or Spain or Greece, and we get lots of ultraviolet, then we are highly susceptible to that ultraviolet light causing damage in the skin. And this is what Fitzpatrick was trying to categorize. He said Fitzpatrick won people are very susceptible to ultraviolet damage and therefore have a greater probability of developing skin cancer compared to all the other Fitzpatricks. And then conversely, Fitzpatrick 6, these people have very high concentrations of melanin in their epidermis, as you can see on the right hand side there. And therefore, their skin is much more protected against ultraviolet light compared to all the other skin tones. So their chances of developing skin cancers are therefore much, much, much lower compared to 1, 2, 3, 4, 5s. All right. So that's what Fitzpatrick was all about. It was essentially a way to determine the probability of somebody developing skin cancer if they were exposed to ultraviolet light. Now, we don't use ultraviolet light. Mostly, the vast majority of skin lasers will not generate ultraviolet light. So the Fitzpatrick scale is no use to us. It's meaningless. But it has been adopted by the medical laser industry. I think probably back in the 80s, I think it was. It was adopted to represent skin color, but it doesn't. That's not what Fitzpatrick meant. Okay, so they've kind of taken his definitions, which is really a probability of developing skin cancer, and they've turned it into something else and for our use, which is really skin color. So I don't tend to talk about the Fitzpatrick. I talk about skin tones. So for me, Fitzpatrick is fine and well. That's good if you're talking about skin cancer, but we don't want to talk about that. We want to talk about skin tone. And the skin tone is essentially like I've got here, the skin color is the concentration of melanin. And for us, that is important because the more melanin in the skin, in the epidermis, means the greater the barrier that the light has to get through. If you fire visible or near infrared light, it's got to get through that skin barrier to get into the dermis, because most of our targets typically are in the dermis, your follicles, blood vessels, tattoos, etc. It's only epidermal pigmentation that is the barrier. It's up in the epidermis. But all the other treatments, we're trying to get through that barrier. So the way I look at this is that the darker the skin, the greater the concentration of melanin, and therefore the higher the barrier that we have to get through. Now, the annoying thing is that this generates two problems for us. The first problem is that the higher the concentration of melanin in the epidermis means as more of the light will be essentially stolen by that melanin and will generate high temperatures in the epidermis where we don't want them. We generally we don't really want these high temperatures in the epidermis. We want the high temperatures in the dermis where the targets are, right? But we have to get through this barrier to reach the dermis. So the melanin in the epidermis steals some of that energy, generates high temperatures in the epidermis, and as a result of stealing the energy, less energy reaches the dermis. So if you fire, let's say, for example, let's say you've got somebody like this, skin tone 1, where very low concentration of melanin, so pretty much almost all the light you fire into the skin will reach the dermis. But then you get this person comes in next for hair treatment or whatever, tattoo treatment, and they've got much, much greater, 10 times the concentration of melanin. So the amount of energy reaching the dermis is much lower compared to this skin. And obviously there's a graduation as you go through the different colors. So when you look at somebody with any kind of color in their skin, you got to think two things. You got to say, okay, this is a greater barrier than I'm used to. This means that the skin color is going to absorb a lot of energy or a certain amount of energy. It's going to generate higher temperatures in the epidermis where I don't want it, and it's going to result in less energy reaching the dermis where I do want it, which is kind of annoying, right? What this means is, are you all sitting down, ladies? I hope you're all sitting. What this means is that in darker skin tones, we actually have to fire higher fluences at the skin to make sure we get enough fluence in the dermis. Now that will be completely opposite to what everybody else has told you in the past. Unfortunately, everybody else was wrong. Okay? I am right, they're all wrong because they haven't considered the physics. The physics is really quite simple. The physics tells us if you've got a bigger barrier between the skin surface and the dermis, then it will steal more energy, it will generate higher temperatures, and less energy will reach the dermis. So the way around that is you fire more energy at the skin surface, but guess what? You're going to get even more energy absorbed in the epidermis and more temperature, higher temperatures, but you'll get more energy into the dermis where you want it. So we have to mitigate against this barrier and these high temperatures, and that's why we use skin cooling. And I'll talk a wee bit about skin cooling both this morning and this afternoon. Okay, so I look at skin color as a barrier. And the darker the skin color, the skin tone, the higher the barrier that we have to get through. All right. Now these are, I showed you that absorption curve for melanin a few minutes ago. That's kind of like a general curve. These are the curves for the different skin tones. Oops, sorry. So if we look at the, oh, sorry, forget these figures. These numbers are old. They've been updated. But this curve down here, this little very, very pale curve, this is for skin tone 1, and that's skin tone 2, 3, 4, 5, and 6. And you can see that as the skin gets darker, the absorption gets significantly greater out at all these lower wavelengths. Fortunately for us, it's not so bad up here where we tend to use our lasers. So if you fire your Q switch ND-YAG, the 532 wavelength, which is the green light, if you fire that at these different skin tones, you can see there's quite a variation in terms of how much is absorbed here by black skin compared to how much is absorbed here as in Finnish skin or Scottish skin, very, very pale. So there's quite a range of absorptions, which results in temperatures, obviously. Alexandrite laser is out here, 755 nanometers, and you can see the range is much, much smaller compared to the 532. So already we're moving into a much, much safer zone. But still, the black skin absorbs a lot more compared to the white skin. And then the diode is out here, 810 is a little bit safer than the Alexandrite. And then out there at 1064, the Nd:YAG, look at that. It's a much, much safer option compared to all these other machines, these other wavelengths, right? And this is why the 1064 nanometer wavelength is the safest, oops, it's the safest wavelength to use on all skin tones. I talk about the 1064 nanometers as being the most benign wavelength because it will do the least amount of damage to all skin tones compared to all the other machines that we use out there. All right. So if you've got, if you're treating a lot of darker skin people, then the 1064 nanometer is the wavelength to choose. If you're treating lots of paler skin people, then the Alexandrite 755 or the 810 diode are perfectly good because you're still down here for pale skins, all down here, very nice. But if you are treating some darker skin, you've got to be very careful with both diode and Alexandrite. All right. IPL does this. You have IPL typically gives a range somewhere usually between 400 and 1200, but we don't use all of that. For if you're using IPL for hair removal, you'll put a filter in somewhere about here, about here, about 640, 650. So that stops all these wavelengths. They don't get through to the skin and only allows just the wavelengths above the filter number. All right, that makes it much safer. Okay, so for melanin, you can pretty much use any wavelength you like in the visible and near infrared spectrum because they all absorb to a certain extent. But if the skin's very, very dark, you run the risk of excess damage, which you don't want. You've got to be careful about the color or the melanin concentration. Okay, just look at skin color as a barrier. That's the way I tend to look at it. The higher the barrier, the more damage it's going to cause. So for blood, the like I said, we target the hemoglobin in the blood, and the absorption coefficient of hemoglobin means we use yellow or green light. For hair, we're targeting the melanin, but we specifically want to target melanin in the deep part of the hair and down in the bulb, as you'll see this afternoon. So we choose red light because red light will penetrate deeply into the skin and still be absorbed. For pigmentation, again, we want targeting the melanin, but this time it tends to be much more superficial, especially if it's epidermal melanin. So we can, again, we can, well, you can use almost any color for that, but we tend to use the lower wavelengths around about 400 or 500 nanometers because they're strongly absorbed. So not much of that light will get into the dermis. It's mostly absorbed in the epidermis in the melanin. So you choose your wavelength according to where your target is and especially the depth. For tattoos, okay, so you've got a whole range of colors these days. So what you need to try and do is choose a wavelength that matches the ink color, and that can be very tricky. We'll talk a bit more about that tomorrow, okay, because that can be quite tricky. But here's a wee video that a friend of ours made. You can see, now let's hope this works. Sometimes this works and sometimes it doesn't. Come on, go, 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 go. Okay, let me move this thing. I don't know why this sometimes does, oops, it is, and sometimes doesn't. Oh, bugger. Right. I've got a link somewhere. I can show you the link. What she's done is she's got this transparent balloon, and inside it she's got a white balloon, red, there's a black one back there, and a wee brown one back there. And she's got an IPL system, and she's put in a certain filter. I can't remember, 590 filter. There you go. And when she fires it through the transparent balloon, the white and the red do not burst because the absorption coefficient is so low for these wavelengths, but the brown and the black do burst. I wish this would quite, it's quite a cool video, this is actually. Uh, dear me. Don't you love it when technology just fails you? That's bizarre. I do have a link somewhere, so I can send you a link and you can check it. It's quite cool. So what that shows is that the transparent balloon doesn't absorb at all. The red and the white balloon, they absorb very, very little, so they don't burst, but the black and the brown balloons absorb enough to cause them to heat up and burst. Very nice. Isn't it great when the technology doesn't work? And then scattering is essentially, it's like one of these machines. This is called I think it's a Pachinko machine from Japan, and they fire in lots and lots of ball bearings, and they bounce off all these wee things all over the place, and that's essentially what scattering is. Okay, but that's kind of like the simple version of scattering. The reality is, the physics of it is actually the atoms will absorb that photon, and it gets excitable, and then it spits it back out immediately. That's what real scattering is. But it's quite difficult to explain properly without going into quantum physics, and I don't really want to go into quantum physics because we'll be here all year if I start doing that. But essentially what happens is the photons absorb, get spat out, but it always goes in a new direction. So very rarely does it go in the same direction that it started. And this is why scattering changes the direction of the photons in all manner of ways, all directions. So here's a wee video that I found online, which is quite cool. If you imagine that this little kind of grey white semi sphere there is one atom, and it's being bombarded with all these little blue photons, then you can see, and this is what happens in the skin, you can see that the photons are going in all directions. You know, they're all over the place, including some of them bounce back up the way, and some might even go vertically, very few, but some might. But you can see how they spread out all over the place. And that's precisely what happens in the skin when the photons encounter atoms and molecules. They bounce about all over the place. And this is why when the light goes into the skin, the beam spreads out. Inevitably, the beam will not stay collimated and keep going as a single beam. It doesn't. It spreads out all over the place. And some of the photons will bounce back, and they will leave the skin entirely. Of course, as the beam spreads out, its diameter increases. And if the diameter is increasing, then the fluence must drop because the fluence is the concentration. And as the beam spreads, it's becoming less and less and less concentrated as it's getting deeper into the skin, and so the fluence drops. So its effectiveness, the heating effect, drops as it goes deeper into the skin as well. So you've got all these problems with the epidermis is absorbing and stealing some of our energy. The epidermis also does a lot of scattering. So a lot of that light that hits the epidermis and hits the melanin will be scattered back out of the skin. And then the light that gets through the epidermis and enters the dermis scatters all over the place and spreads out. So the fluence and the concentration drops accordingly. So we've got, honestly, whoever came up with this idea of using lasers in the skin was bonkers, because it's not a great idea. But there you go. And then we've got how light penetrates the skin anyway. Different wavelengths penetrate to different depths. Okay, so your very blue, like ultraviolet down here, and blue light, they don't really go that deep into the skin at all. Superficial dermis at best. Green and yellow light can penetrate a little bit deeper, to maybe down to the kind of upper reticular dermis, and then red and infrared light will penetrate the deepest. So what this means is, if you want to treat, let's say you want to treat blood vessels, you're using your green and yellow light, which are strongly absorbed in blood. But if your blood vessels are down here, then forget it, because the light just can't get down there unless you fire in huge amount of fluids. But then that could cause all kinds of damage up here. If you want to fire red light to target these blood vessels, well, that's great. But except the problem is that the red blood will not absorb red light. So that's kind of pointless too. So when we're firing light into the skin, you've got to ask two questions. First of all, how deep is the target? Can I reach it with this wavelength? And secondly, if the light does reach it, will it be absorbed? Because you can fire red light at deep red blood vessels and nothing's going to happen. Forget it. Waste of time. There is a caveat to that, which I'll come on to that tomorrow, though. And then there's other things when you fire light into the skin, there is a certain probability that it will be absorbed by anything in the skin. So even though you might fire, say green light, and it hits a water molecule, well, the chances of it being absorbed by that water molecule are very small, but not zero. So some of those photons, if you remember how many photons, it was 5 bazillion photons, some of those photons will be absorbed by the water, even though the probability is very, very low. Some of the red photons will be absorbed by blood, even though it doesn't like red light, and even though the probability is low, but it's never zero. That's the thing. So when you fire all these different wavelengths into the skin, some of the photons will be absorbed by other targets that we don't necessarily want to be absorbed by. So keep that in mind always. It's not just a case of, yeah, this light will only be absorbed by melanin or only be absorbed by blood, because that's not true. It's absorbed by everything. And then you get this effect. So when imagine you fired light at your skin like this, and you've got bones and nails and hair and God knows what else. Well, some of that light, as you can see here, will be transmitted because it's scattered around. So you can see the yellow here. Okay, so the yellow light is basically light just getting through the gaps. Okay, so that's easy. It's a yellow light source behind there. So the yellow light's just kind of pretty much going straight through. But you can see, look at how the skin is all illuminated here. All that red, that appears like red light. And what's happened there is that the light has gone into the skin and it's scattered all over the place, scattered all round, and then scattered off the atoms and the molecules in the skin, and then re-emerged. And we have this kind of this red appearance. The reason it's red is because the blue and the green and the yellow are pretty much all absorbed or scattered back out the way, and they don't transmit all the way through, except for the yellow in the gaps here, because that's obviously that's a much what we call optically thin region, so that the light can just kind of sneak through. But certainly for the bony regions, like here, obviously the light can't get through the bone, but it can scatter all the way around and re-emerge, and pretty much only the red light gets through. All right, so there you go. That's transmission and scattering and absorption and all kinds of things. So backscattering, this is actually one of the kind of topics that's not talked about very often, and it really should be, because when you actually look at the amount of backscattered light, it's significant. So in this little model, all the red arrows are the light that are forward scattered and going into the skin. The blue arrows are the photons that have turned around and are now heading back towards the surface, and the big blue arrows are the sum of all the little tiny ones, we can lose up to 60% of our light through backscattering. That's a significantly high number when you think about it. If you're firing all this energy into the skin and 60% is turning around and coming back out of the skin, then we're only getting 40% in the skin. And then some of that's going to be absorbed in the basal layer, maybe 5% perhaps. So only 35% of your light that you're firing in is actually ending up in the dermis where we want it. 35%, that's just over a third. That's not good at all. But it does depend on the wavelength. So what we found is that your red and infrared light can be up to 60%, but the green light that we use for the Q-switch YAG 532 nanometers wavelength, that's only about 30%. So green light tends to be more better retained within the skin compared to the red, and it varies between those numbers for the different wavelengths. So backscattering is a significant amount of energy loss. We do have to account for this. Kind of annoying. And then so I did this. This is my arm, and I fired a laser at it. And what you're seeing here is essentially that kind of white region there is the reflected and backscattered light from the laser dot. So this is a red laser. And the reason it appears white is because so much light is reflected at the surface and backscattered that it saturates the camera in my phone. So it overloads it. That's why it turns out white. But look at the backscattered light. Look how large that region is. Okay, so that's light that's getting into the skin here and scattered about internally and then re-emerged through the skin surface. It's huge. I mean, it's probably somewhere like maybe 10 times the area of the original spot. That's a large area, as you can see there. And that's just the stuff that the camera's picked up. There's probably more backscatter light out here that the camera hasn't registered because it's so low. So this zone can be quite large. This is why you've got to be careful when you're treating, for example, if you're treating hair with a diode laser, and you go near a tattoo, if that tattoo is too close, say here, then you could get a significant amount of energy hitting the tattoo, and that can cause damage. And I've seen that happening. People have gone just a bit too close. So I normally say to people, stay about maybe 3 centimeters away from a tattoo if you're treating hair, because 3 centimeters, although it sounds huge, this light can transmit internally through scattering quite easily, as you can see there. And that's just stuff we can see. So backscattering is not only is it significant in terms of loss of energy, because a lot of it escapes, but also in terms of where it goes internally and whether it could affect other targets that we don't want affected. All right. So when we look at this in reality, you remember that I showed you a wee graph a wee while ago that showed you light going like this in the skin. It's an exponential drop. Well, it doesn't do that in reality. Well, it only does that if there's no scattering. If it's purely absorption, then it does an exponential thing. But when you add in scattering, this is what really happens. You get this effect. So you get light going into the skin, and it's forward scattered into the skin, and then it bounces about, and then it meets backscatter light coming out of the skin while the pulse is being delivered, because this happens very quickly. So then you get this accumulation where the forward scatter light meets the back scatter light. You get an accumulation of fluence there, because you've got all these photons coming from all directions. And this is my friend in Gothenburg who did this, did some calculations, and this blue line here, this is 1064 nanometers. So you can see it's quite high here, and then it drops. The orangey light is 755 alexandrite, and then I've added this red dotted light. That's the average of these two, and then the green light is that's 532. Now you see this red dotted line here. This is the fluence that was fired in, or the relative fluence, 100 joules per square centimeter. And look what's happened. The green light has backscattered so that it reaches about 50% more than the initial light, but these guys are more than double. So this is very strange. This is not intuitive at all. What this is telling us is if you fire in 100 joules, or if it's 10, let's say 10 joules per square centimeter, then for these wavelengths, the Alexandra and YAG, down to a depth of about nearly 1.5 millimeters, there is more fluence in that superficial layer of skin than there was being fired in, right? And you think, how the hell can that happen? It's because fluence is additive. The fluence coming in is meeting the fluence coming out, and so it adds up. You get this accumulative effect. Even for the 532, it's not as bad as for the infrared wavelengths, but it still adds up down to a depth of about what, zero point 0.4 millimeters, something like that. So what this is telling us is that in the superficial layers of skin, there's an accumulation of fluence there which could potentially cause more damage, especially in the basal layer where you've got all that melanin. So we have to account for that. We've got to say, well, hold on a minute, this could cause a lot of unwanted damage in a region where we don't want any damage at all in the epidermis and in the basal layer. So this is a well-known phenomenon. This has been known for like 30 years. Um, and it replaces that curve I sort of showed you, the exponential curve. No, that's kind of pie in the sky imaginary stuff. This is the real effect, because you have to include the backscattering effect with the forward scattering, and it all adds up, and it just makes life just a little bit more complicated. But in actual fact, it can help us as well, though, because knowing this, you can calculate the fluence you need to fire at the surface to achieve certain fluences at these depths here. Say you're targeting blood vessels or hair follicles or whatever. So this is actually very, very useful stuff to know. Yeah, 100 is the fluence at the skin surface, or so that could be 10, it could be 5, doesn't matter. It's just a relative number. Okay, that's for 532, and that's for I told you all this stuff already. What, nearly 1.5 millimeters deep for Alexandrite and Indiac. So in summary, we've talked about absorption, where the light is absorbed and generates heat. Scattering, and you now know how important scattering is. Scattering causes all kinds of issues and problems and reduces the fluence as you go deeper into the skin. Backscattering is when we lose all that energy when it comes back out of the skin surface. Not great at all. Absorption is eventually any light that's in the skin that is absorbed is scattered light. It has been scattered. Now, curiously enough, just the way the physics works, it might have only been scattered one occasion, one little photon hitting an atom. It's scattered once, and then it's absorbed by another atom. Hey presto. More likely, it will have been scattered many, many, many times, thousands, millions of times potentially, before it's finally absorbed by something. It doesn't really matter, but all absorbed light is scattered light. It's all probabilistic. In other words, um, every time the photon hits an atom, there's a certain probability that it'll be absorbed and a certain probability that it'll be scattered. That's the way these things tend to work. And it's the absorption that directly determines the temperature rise. So the more absorption you get in a target, the higher the temperature rise. Everything in the skin will absorb something. Like I said before, doesn't matter if it's water, keratin, hemoglobin, whatever, they will all absorb some energy. So the background temperature will rise. Now, it might only be by half a degree, or it might be 2 degrees or whatever. Quite often it's not significant in most situations, but the target that we're going for, if it's hemoglobin or melanin, the temperature should rise significantly, which is what we're trying to do, right? Scattering, the dermis is a highly scattering medium. Now, it's kind of curious. I've seen people online saying, I don't know why they say this, but they say, oh, the skin doesn't scatter much at all. Yes, it does. The dermis is very highly scattering. So don't listen to that nonsense, right? As soon as light enters the skin, it scatters. It just, poof, off it goes. Can't help it. And as a result of the scattering, the beams spreading out, the fluence drops rapidly with depth. And that's when your treatment stops. If your fluence at skin surface is low, then it doesn't take much scattering for it to drop to below threshold, and it won't do anything anymore in your target. So the fluence will hit the target, but it's so low that it just doesn't generate enough heat. Okay, so the way around that is by increasing the fluence at the surface. Backscattering, we lose a lot of energy, potential up to 60% with the infrared wavelengths. The shorter wavelengths are not quite so bad, fortunately. And the backscattering increases the fluence in the upper dermis and the epidermis. So we've got to be careful about that. Again, we don't want to cause unwanted damage up there. So we've talked about fluence, wavelength, pulse rate, pulsation, etc., absorption, scattering, and backscattering. All of these are important in all light-based treatments. Doesn't matter what you're doing, what you're treating. It doesn't matter if you're treating hair or cancer, or if you're doing PDT with LED systems or whatever. These are all important events, okay? Or parameters. You need to understand what they're doing and why they're doing it. So if you don't understand it, please go over this recording again, and you can go through all that stuff, or you can look at the stuff in my book. You know, there's all the stuff in the book. The bit of just a wee bit of fun here. The electromagnetic spectrum is huge. It is absolutely enormous. We only see a tiny, tiny sliver of that, which is this wee bit here. That's the visible spectrum. But below our visible light, we've got your ultraviolet, X-rays, gamma rays, cosmic rays. These are all exceptionally dangerous. Well, gamma rays and cosmic rays, they'll kill you pretty quickly if you get exposed to them. And then above the 700 nanometers or thereabouts, you've got all the infrared stuff, and that includes your microwaves, radar, radio, TV, GPS, all this kind of stuff, all the broadcast stuff, whatever. And your the wavelength of that can be, look at that, you can have a 1 kilometer or even 10 kilometer wavelengths of light out there. It's you can call it light, call it what you like. It's light, but it's invisible. It's all electromagnetic stuff. And of course, the good thing about infrared light is it can show you things that we can't see with the human eye. So this chap was recorded using an infrared camera, and he's, for some reason, he's ejecting some warm liquid, because you can see the heat from the liquid. And also at the same time, he's ejecting some warm gas. Now, you wouldn't see that with the human eye because we can't see infrared, but the camera picked up, so he was caught and nailed. One of the benefits of infrared light. There you go. All right, so that's the first session. Oh, we're going to talk about it in the next session. So do you want to have a wee Q&A just now, or do you want to take a wee break and then pick up later on, or what? Need to switch on a microphone, somebody. Are you still there? Hello?
Yes, we're here. We could take a break now and then
We'll take a wee
continue
break.
after the, yeah.
Right, okay. So in Scotland it's 11:20, so it's 1:22 over there. So shall we come back in half an hour then at 10:02? 1:50. We can do the second section.
Sounds cool.
Yeah?
Yeah, half an
Okay,
hour.
half an hour. Excellent. All right, so see you guys in at 10 to the hour. Okay?
Yes. See you.
I'll stop the recording now and then restart it next time, okay?
Bye.
So in this wee section, this is relatively short. We'll finish off with lasers, an introduction to actual lasers. Here's the very first machine that was ever built by a chap called Theodore Maiman back in May 1960. So lasers are not actually that old. He built a ruby laser. There's a little ruby crystal in there. That's that little bit in there. And there was a little reflector on there, and a reflector here, and a helical lamp, and out popped some ruby laser light. And the story goes that he did this, and it was in the AT&T labs in Chicago in 1960, and he built it and got it working and all that, and called all his engineering friends all round and said, look, I made a laser. And they're going, ooh, look, a laser, ooh. And then a wee guy at the back said, excuse me, what does it do? And they're going, yes, good question. We don't, and they had no idea what to do with it back then. Now, of course, we use lasers in all manner of things out there: scientific, industrial, medical, laser shows, and what have you. There's a huge number of even things like CDs and DVDs, if you remember those, if you're old like me. So what are the properties of laser? Laser light is unique. It is purely a human invention. That there are no natural sources of laser energy in the entire universe that we're aware of at the moment. Maybe there is, but at the moment we don't know. So there are three things that make laser light special. One is that it's monochromatic. In other words, it has a single wavelength, a single color. The other one is it's got minimal divergence, which means the beam doesn't spread out like ordinary light does. It's very kind of focused or collimated, we call it. And then finally, they are all little waves are highly coherent or in phase, a bit like these soldiers who are all marching in their wonderful uniforms, and they all march at exactly the same speed and in the same direction, and they're all looking at I don't know who they're looking at, some bloke over there on the left-hand side. So these guys, they're all highly coherent, and laser light is kind of like this. The waves are all very, very in phase, and they're all going in the same direction and in the same wavelength and same everything. Highly coherent. Whereas what this means is we can then focus these energies into very, very small areas, which you cannot really do with ordinary incoherent lights. It's very difficult. Lasers is very simple, just a little lens and you're away, no problem. So you look at a laser beam. Now, you prepare to be amazed by my fantastic graphical abilities. A laser beam like this is monochromatic. It doesn't diverge very far, and it's highly coherent. Whereas an IPL is more like this. You have lots of different colored lights, different wavelengths. It's completely incoherent, and it diverges all over the place. So it spreads out everywhere. So you might think that IPL's a waste of time, but it's not, because even with all this multicolored, incoherent, divergent stuff, we can still generate a lot of energy in an IPL beam, and it still is very useful in the skin. So we can't you can't write them off. And IPLs have been around since about 1990, and have been very successful in a lot of treatments out there. So one of the things though that I hear often, people say, well, IPL is not laser, so it's no good, it's rubbish. Once it goes in the skin, it becomes useless. But these people are talking garbage, because if you look at what laser actually is, so in the air, laser light is monochromatic, but in the skin, as soon as it hits the skin surface, it starts to scatter. It also goes through a refractive index change, because the refractive index of the air is about 1.0, but in the skin it's about 1.4 or something like that. So once the light goes into the skin, that change in refractive index causes the beam to slow down. The light slows down. It's no longer at the speed of light in the air, just under the speed of light in the air. Once it goes into the skin, it slows down because it's hitting all these atoms and molecules, and that just slows the overall velocity. And because of that, the wavelength drops. So if you fire 1064 nanometers into the skin surface, when it enters the skin, it slows down and the wavelength drops to 800 nanometers. Isn't that surprising? All the wavelengths do that. They all do. They all slow down. And then if it backscatters out of the skin and leaves, it goes from a high refractive index back into a low refractive index. It speeds up again, and the wavelength extends back up to 1064. And that's a surprise. In the air, it's minimally divergent. In other words, you can point a laser across the room and have little dots on the wall, and you can annoy the cats and the dogs and the kiddies. But in the skin, because of the scattering, as soon as it hits an atom, the photon bounces off in a different direction, and the beam spreads out rapidly. And therefore, the beam becomes very divergent. So it loses its divergent properties as soon as it hits the skin. And then in the air, it's highly coherent. All the waves are all going in the same direction and in the same phase and all the rest of it. In the skin, every single time it scatters, it loses its coherence drops, and eventually it drops to zero. So the laser light in the skin is completely incoherent. So in other words, it's no longer laser light in the skin, because it's the wavelength is still monochromatic, but it's a different wavelength to when you fire it in. It's no longer minimally divergent because it's going all over the place, and it's no longer coherent because it's scattering everywhere. So my argument has always been the case that once that laser light enters the skin, it is no longer laser light. It's just light of a particular wavelength, but it's kind of like ordinary IPL light or sunlight or whatever other source of light. It's not laser anymore. Even when it comes out of the skin, you can't even call that laser, even though it goes back to its correct wavelength, because it's going to be scattering in all directions when it leaves the skin surface. So what are the four interactions that can occur in the skin? Well, we've got a photothermal, where the photons generate heat, so that's the thermal part. We've got a photomechanical, where the photons don't have enough time to generate heat, but they create a mechanical physical disruption, usually in tattooing, but also in melanin as well, in fact. Photoablation, this is when we boil tissue water and the skin comes flying off in all directions. That's what CO2 laser. And then photochemical, which is a much, much more gentle process where the photons stimulate certain elements within cells, usually mitochondria, and that creates a certain kind of reaction, but it's very, very subtle. You don't feel anything. There's no heat. There's no physical sensation. It's a very, very subtle process. So photothermal treatments, we tend to concentrate on hair, blood vessels, acne, and pigmentation. Photomechanical, we can use that to treat both tattoos and pigmentation again. So pigmentation actually can be treated by a wide range of lasers, and we can use either the photothermal reaction or the photomechanical reaction. Photoablation, we tend to use CO2 and other machines to give us resurfacing and scar revision and such likes. And then photochemical, low-powered, usually LEDs or low-powered laser diodes. And we can use that for rejuvenation, smoking cessation, muscle healing, and what have you. Okay, so these are the four main interactions in the skin. The sorts of treatments that we do in the main tend to be the top three. Photochemicals is I mean, some people do that. I've never really been involved in photochemical. It's just a bit too subtle for me, I'm afraid. So with photothermal treatment, it's a gentle heating in a sense. So we use quite long pulses, typically milliseconds, which to me that's a long pulse compared to nanosecond or picoseconds, right? And so we can treat hair, vessels, pigmentation, tissue water, etc. Photomechanical, we use much, much shorter pulses, typically nanoseconds or picoseconds. And that's a much more aggressive heating because there's no time for the heat to escape at all in a nanosecond or a picosecond pulse. The pulse is far too short. So all the energy is turned into heat. So you can generate very, very high temperatures in for example, tattoo ink or melanin. So we tend to use that for both tattoos and pigmentation. Spot size, people get a bit confused about spot size. Which goes deeper, large spots or small spots? And it's not exactly intuitive. If you fire a large spot diameter into the skin, then you will get some kind of a fluence distribution like this, where it's quite hot near the surface, then it gets a bit cooler as you go deeper and deeper and deeper as you go further from the spot. But if you fire a small spot with exactly the same fluence, then this is what you find. And we've found this through both numerical modeling programs and also clinically. You can see through histological evidence. So if you've got the same fluence firing at the surface, then with a bigger spot, you get a deeper effect compared to a small spot. So what this tells us is if you're targeting deep things like hair follicles and blood vessels and what have you, then you should always try and use as big a spot as possible to get enough energy deep down there into the dermis. All right. And this effect is entirely due to scattering. That's why small spots don't penetrate as far as big spots. Okay. The temperature rise, right? Are you all ready for this? I hope you're all sitting down because I'm going to throw a wee equation at you. I love equations. Okay, they are my bread and butter. I love mathematical language more than I love English because English is a terrible language, but maths is a great. I love maths, man. So remember mu, we spoke about that earlier on, with mu A and mu S and what have you. That's the absorption coefficient. So that tells us how strongly something is absorbed by the target. H is the symbol we use for fluence. Why we don't use F, I don't know. It's H. It's a bit bonkers, but there you go. I didn't choose it. So mu times H, that tells us how much energy is absorbed in a absorbing target, right? And then to calculate the temperature, we then have to consider the density and the specific heat capacity of the material. So there you go, absorption, fluence, density, specific heat. And if you do this equation and you calculate it for it could, melanin or water or whatever, then you can calculate what's known as the instantaneous temperature rise. So you can see quite clearly here, you can see rho c is a constant. You can see quite clearly here that increasing the fluence will increase the temperature rise. Increasing the absorption coefficient by changing the wavelength will also increase the temperature rise. Or if you choose the wrong absorption coefficient and it's low, then the temperature rise is also going to be low. So the two things, we can't control these guys, rho C, because that's to do with the tissue. We have no control over that at all. But we can control the fluence by changing the parameters on the machine, and we can control the absorption coefficient by choosing the correct wavelength. Okay, so that's why we want to match the wavelength with the absorption coefficient to get the highest temperature rise. Okay, mu is essentially the color, you could say, of the target. So blonde hair has a very low mu, so therefore the temperature rise in blonde hair is inevitably going to be very low, and that's why we can't really treat blonde hair, because the absorption coefficient is so low we just can't get enough energy into the hair. And the reason for that is that the concentration of melanin in blonde hair is very low. Here's something you might not know. Hair color is determined by the melanin. Black hair has very high melanin. In fact, I'll show you these guys here. Black hair has got the highest concentration of melanin, therefore the highest absorption coefficient. Brown hair has a lower concentration of melanin, which is why it appears brown. And blonde hair has one of the lowest concentrations of melanin. But believe it or not, blonde hair could be viewed as a very, very pale black hair. Isn't that interesting? It's just to the human eye, it looks yellow because of the way we perceive things. But in actual fact, blonde hair is just a pale black hair or pale brown hair. And then you get white and grey hair. I have one or two up here somewhere. I'm sure I can find them somewhere. And they have almost no melanin in them at all. But tell me this, why does this hair here have no melanin and yet here I've got tons? Look, why just it's like 3-4 centimeters. What the hell's going on there? I wish somebody could tell me. So the temperature rise is determined by the fluence. You can once you've chosen your wavelength and your machine, whatever gives you such and such nanometers, you can choose the fluence to influence the temperature rise. Now, where most people tend to go wrong in treatments is they tend to use a low fluence because they don't want to burn, they say. I don't want to burn my patient. So they choose a low fluence. Consequently, they get a low temperature rise and therefore they don't get a good reaction. And then they wonder why it doesn't work. You should learn a little bit of physics. That's what you should do. Right, so if we're generating all this heat in the skin, then you've got to balance that with cooling. So I'm going to talk a wee section of cooling now. Basically, the way this works, quite simple. Skin color, like I said, is a barrier. If you have a pale skin color, then you don't get too much heat generated, so we don't need much cooling. If you have a dark skin barrier, skin tone 6 or something, then you're going to get a lot of heat generated in it, so we need a lot more cooling. So it's as simple as that. Pale skins, not much cooling. Darker skins, much more cooling. Keep that in mind always. There's more melanin in the darker skin to absorb the light, hence more heat is generated and more damage potentially, okay? And because of that, less energy actually gets through the skin, through the epidermis into the dermis, right? We cannot overcool. This is a curious thing I only realized a couple of years ago. People used to say to me, oh, but what if you overcool the skin and you make the hair cold as well? And what I realized was, no, we can't, because if you're treating darker hair, you should only ever treat dark hair, right? Dark brown and black hair. The concentration of melanin in the hair is significantly greater than the concentration of melanin in the epidermis. So if you're looking at a pale skin person, skin tone 1, skin tone 2 or something like that, and they've got black hairs, then the hair can have 20 times the concentration of melanin compared to the skin, the epidermis. So even if you take the skin down to nearly 0 degrees with your cooling, the hairs will still absorb a lot of energy because they get so much melanin and they will become hot enough. So it's almost physically impossible to overcool the skin for laser hair treatment. So don't worry about if you cool too much. You can't really cool too much, okay? So, but the only problem is we've got all these different skin tones from very pale up here to very dark down here. And you're going to say, so what you fire some energy, some fluence at the skin, what are the temperature rises? Well, I did some calculations just to see what this is. So for this lady, if you fired in, I've lost the, yeah, if you fire in a certain amount of energy, certain fluence, her skin temperature may rise by about 5 degrees. if we assume her skin temperature starts at 35 degrees for all these ladies, then that means her skin temperature will go up to about 40 degrees. Okay, fine. Oops, for this lady, she's got slightly more melanin, so a slightly higher temperature eye, so she'll go up to 42 degrees. This lady, though, oh, she's got a lot more melanin, 3 times the concentration of this lady, so her temperature increase is 15 degrees. So she's now at 50 degrees. Now, the thing is, your pain receptors, they're called nociceptors in the skin, trigger at 45 degrees. So while these ladies don't feel pain because they're below 45, this poor lady will feel pain, even though it's the same fluence. We haven't changed anything, same fluence, same wavelength, same pulse, same everything. It's just her skin color that's changed the temperature rise. This poor lady, she's in even more pain because her rise got 25 degrees, so she's up at 60, and then this poor lady is running, screaming down the street, calling it all the bad names in the book because her temperature, skin temperature, is now 67. The pain kicks in at 45, so she's in a lot of pain. And it's interesting that I read recently that the pain receptors trigger at 45 degrees, but the speed of response depends on the temperature. So if you have a low temperature, like say 47 or 48 degrees, then it takes quite a long time for those pain receptors to trigger. Something like half a second. It's quite slow. But if the temperature is like this, 67 degrees down here, then they trigger very, very rapidly, much faster than for low temperature. So basically, the problem is that as the skin color gets darker, the temperature rise in the epidermis is greater, and therefore you easily go through the pain threshold and it becomes painful. Okay, so this is why we need to use cooling. Absolutely important. And if you increase the fluence, these temperatures get even higher, so that's even worse. Right? So here's the cooling idea. There's your basal melanin layer just below the epidermis. That's where all your epidermal temperature rise is going to go, depending how much melanin there is. And then the germ cells in the hair are going to be found in the bulge here and around the papilla here in the matrix. There's a lot of melanin in the matrix, actually. In fact, up to 5 times the concentration in the matrix compared to the hair. But we'll talk about that in the next session. So what we're trying to do is the current thinking is you're trying to raise the temperature of the papilla cells, because the derma papilla is the control center for follicles. It sends out all the signals to grow and die and to stimulate the stem cells, etc. We'll talk about that later. Right? So, oops, it easy. So what we need to do for cooling is we're trying to cool this layer because the pain receptors are all up here, the nociceptors. And if there's no cooling, then it only takes a 10-degree rise from your base skin temperature, 35 to 45 degrees, and you're in pain. So that's no good. We don't want that. We want the heating to go on down here, not up here. So that's why we apply skin cooling in advance. I normally recommend you do ice packs on the skin surface for 2 minutes, and then that'll cool down this whole region to quite some depth, actually. And it'll make it much, much safer and much, much less painful as well. But there are limits. So this lady, she's a model from, I think she's from Sudan, very famous international supermodel. And look at her skin tone. It's a beautiful, really, really kind of almost blue-black sheen of her skin, because she's got extremely high levels of melanin. This is just too dark to cool. We cannot cool her skin sufficiently, because it doesn't matter how much you cool it. You can only cool down to 0 using ice packs. You can't go below 0 with ice. If you raise the temperature from 0 up to 45, she'll feel pain. And with the amount of melanin she's got in her skin, it'll probably exceed 45 degrees. So we just can't cool some skins. They're just too dark, okay? Selective photolysis, you've probably heard about this. This is a theory that underpins a lot of today's laser treatments in the skin. It was created by Anderson and Parrish way back in 1980. And the idea of this theory is that you want to selectively damage just the unwanted tissue. So that could be hair, or it could be blood vessels, or whatever. But you want to leave the adjacent tissues undamaged. That's the whole idea of this principle. To do that, they said, let's match the wavelength with the target's absorption peak, where it absorbs the best, the strongest. Choose the most appropriate fluence, depending on the size of the target and the depth and what have you. And you choose the pulse duration to match its target size. Okay, fine. And then they came up with this idea of thermal relaxation time. And the principle was, if you fire your laser energy in a time less than or equal to the relaxation time, then most of the energy will be retained by the target and the temperature will go up. And hey presto, you get all your results. That's all fine and well. Yep, that's groovy, but it kind of missed something quite important. They didn't realize at that time that that's kind of like half of the equation. You're trying to heat up some targets. Okay, but you don't just want to heat it, you want to cook it. Okay, so if you let's say you're boiling an egg and you put a pan of water onto the cooker and the water's bubbling away. So once it starts to bubble, you know it's reached 100 degrees Celsius, right? That's your energy density, your fluence, because you know how much energy is enough to boil water. So that's a good fluence. Okay, you then put your egg in and you take it out after 15 seconds. It's not going to be cooked. Or what will happen is the very outer edge of the white of the egg, the albumin of the egg, might be cooked, but most of it will not be cooked. Because even though you've put it into the correct fluence in the boiling water, you haven't left it in there long enough, right? And this is where the relaxation time argument falls apart, because if you're trying to cook the germ cells, or the stem cells rather, in the papilla or in the bulge of a hair, then they need a certain amount of time at a certain temperature to cook properly. If you just get the temperature up and it drops, they just won't cook. You know, you might cook maybe a few percent, maybe 10% perhaps, but 90% remain, and that follicle will regrow. So the relaxation time argument doesn't apply to hair follicles. And I'll come back to it in a second, sorry. And I wrote a paper on this a few years ago with my Swedish friends and got it published because we realized that people were sort of fixated on relaxation time. But in actual fact, if you read back to Anderson and Parish's original papers back in 1981, it is actually quite an arbitrary choice. They had to choose, they knew you had to deliver the energy in a relatively short pulse, but they didn't know how short a pulse. And they chose one relaxation time because it was mathematically it was a kind of an obvious choice, and from the physics it was fine, it was okay, but biologically it's not good. So while we've been using that for years and years and years, it doesn't explain why we can treat hair follicles of different sizes and different depths. Relaxation time just doesn't work for hair follicles. It does for blood vessels, which is how they designed it originally. But when you translate to follicles, it's a different situation altogether, which I'll talk about more this afternoon. All right. So selective photothermolysis is a bit like this. You fire in your photons at some target. Doesn't matter what, it can be melanin or hemoglobin or whatever, tattoos, and you're trying to raise the temperature of that target, and you have to keep it above, well, if it's proteins, so melanin, hemoglobin, etc., you have to keep it above 70 degrees Celsius for a certain length of time to achieve a sufficient amount of cell denaturation. If you don't keep it up above 70 for that length of time, you will only kill a few cells and the target will survive and grow back. If you set a temperature to 60 degrees, then you need an awful long time to cook the cells. 60, just forget it, just won't work. Conversely, if you push the temperature up to 80 degrees, then the amount of time you require shortens significantly. It's much shorter. That's why higher fluences is better, because a higher fluence will give you a higher temperature, and a higher temperature the cells will cook much faster compared to lower temperatures. This is why I always talk about high fluences, always. Relaxation time. What is relaxation time? If you look at it, the actual proper technical expression, it is the time required for a peak or a maximum temperature to fall to 37% of that value. Now, That's all fine and well. It's a great physics description, but it does not match the biology because it doesn't depend on what that peak or maximum temperature is. So if that maximum temperature was 60 degrees, then the relaxation time is the time it takes for it to fall from 60 to whatever 37% of 60 is. But if it's 100 degrees, then it's the time taken to fall to 37 degrees. If it's 1,000 degrees, it's the time taken to fall to 370 degrees. So the absolute temperature doesn't matter with relaxation time. It's a relative measurement, not absolute. The problem is that when you're denaturing or cooking cells, it's the absolute temperature that matters, not the relative temperature. So this is why the relaxation time argument kind of falls apart for hair follicles. And so we just ignore it. It's irrelevant for what we need to do. Fortunately, it doesn't really matter anyway, because most devices nowadays will deliver pulses which are significantly longer than the relaxation time of the target. So we don't really care. But essentially, relaxation time is a cooling time. Now, tell me this: all of you ladies out there who bake cakes, I'm sure you all do. I'm sure. I hear Finnish cakes are delicious. Oh, that's what Vera told me. Vera left me some nice Finnish chocolates and this kind of yellowy ball thing. I can't remember what you call it. Very nice. I haven't finished them yet. So if you bake a cake, right? You mix up all your ingredients. You put it into a baking tin and you put it into the oven. You do not cook it based on its cooling time, do you? You don't say, well, the cooling time for this cake is 30 minutes, so I'm going to bake it for 29 minutes. That's absurd. Why would you do that? But that's exactly what this idea in Lasers and Skin is all about. You say, we choose our cooking time, the pulse width, according to how quickly the target cools. Why? It actually doesn't make an awful lot of sense. It was a convenient kind of placeholder, you could say, back in the day. But the reality, in those days when Anis and Pasha did this stuff, the laser pulses were extremely short. They were less than they were down in the microsecond, less than a millisecond. So they didn't really have long pulses to play with. So it was kind of fortuitous and convenient. They said, well, it needs to be a short time. Hey, look, the lasers do short pulses anyway. Fantastic. And then when we started to use longer pulses and in particular IPLs, suddenly the pulse lengths were much longer than the relaxation times. And it didn't make sense anymore. And that's because the relaxation time is not actually that important. So forget about it. They say choose a pulse width to match the relaxation time. No, it's just wrong. Okay, so this is the paper we wrote back in 2013. Published it in Lasers in Medicine and Science. There you go. Myself and P.A. Torstensen. So denaturation time. This is the more important, not relaxation time, it's the denaturation time we should consider. And that's the time required for the cells of the tissues to be irreversibly cooked, denatured. So they are dead, so they cannot regrow. Like I say, you wouldn't bake a cake according to its cooling time. You bake it long enough to cook all the ingredients. So that could be an hour or 90 minutes or whatever. It's a cooking time as against a relaxation time, which is a cooling time. It's a much more sensible way, right? Often people talk, they assume that the pulse width is equal to the denaturation time. That's not true either. There's no relation between the pulse width and the denaturation time, and it actually doesn't matter. Right? So don't worry about stuff like that. Okay, it kind of confuses people. A lot of people out there are confused and they get all, oh, but don't worry about it because it's not important. Okay. To effectively kill the target cells, we must cook them properly. All right, you want to have your fried eggs cooked all the way through. You don't want some half-cooked fried egg because you'd send it back because it'd be horrible. The cooling time is completely irrelevant. Who cares how long it takes for your fried egg to cool down? As long as it's not too long. You don't want to eat a cold egg. Yuck. So the reality in all these treatments is that fluence is the critical factor. The fluence is what drives the whole process, whether it's hair removal or tattoos or anything, pretty much any skin treatment. It's the fluence that's critical. The pulse width really is kind of trivial. It's just not that important, okay? And relaxation time, forget about it. Who cares? So that's the kind of physics. Got a couple of slides left for this wee section. safety glasses are critically important, right? You got to use the right glasses, and people get a bit confused about this. In the EU, it is absolutely mandatory that you wear the correct glasses for whichever laser you're looking at. The glasses safety factor, they depend on the wavelength and the power output of your laser. So the glasses have to be aligned with both wavelength and power of your machines. We use something called the optical density scale, which is how thick the glass is to particular wavelengths. And you'll see on the glasses or on the frames all these numbers and letters and what have you, and they tell you exactly what this optical density and wavelengths and all the rest of it. An OD, optical density of 7, means it's got a 10 raised to the power 7 protection level. In other words, 10 million protection level just for that wavelength, though. Just for that wavelength. You could have an OD7 for like 1064, like in these glasses, but it might be OD2 for I don't know, 600 nanometers. So an OD2 is only a 100 protection level, which might not be enough. That could be damaging to your eyes. Okay, you've only got one pair of eyes. Make sure you protect them properly. The laser class system tells us which classes to use. If you get class 1, 1M, or 2 or 2M lasers, these are kind of little laser pointers. These are very safe. These only go up to 1 milliwatt, and you don't need safety glasses for any of these guys. Once you get to class 3R, you're talking 1 to 5 milliwatts. Now it's becoming a little more dangerous, especially at 5 milliwatts. That could cause some damage. But once you get to class 3B, now you're getting up to 5 to 500 milliwatts. These are dangerous. You do not want to be looking at these kind of lasers without proper glasses. And in class 4 is everything above 500 milliwatts. These are severely dangerous. If one of these gets flashed into your eyes and you're not wearing the proper safety glasses, they could easily cause damage, potentially even blinding you, especially high-powered systems like Q-switched and picosecond lasers. They're extremely high-powered. They can blind you quite easily, so always wear your glasses. Right, so to finish off this wee section, photothermal treatments. All photothermal treatments are a balance between the heating side of it, which you gain from your fluence, and the cooling side to protect the skin. You've got to get that balance. If you don't get the balance right, you're going to cause too much heating and you could damage the collagen and create scar tissue. If you have too much cooling and not enough fluence, you're not going to get any result at all. You're just going to get a nice cold skin, but no results. Okay, so it's all about getting the balance correct between these two things. Okay, there's my book. I think some of you've seen it. That's the, what do you call it? The QR code. You can there's a free online version. You can have a look at a PDF version. I do sell them as PDFs. I did have physical hard copies, but unfortunately I've sold out of them, and I haven't printed up new ones yet. I will one of these days. I'll get around to it. If you read this book and understand it, this is just purely about the fundamentals of the technologies and all these kind of things we talked about today. You will understand much more about how they work, and you will get better results, I guarantee. Right, so that's the end of this wee session. We talked about energy, fluence, cooking tissues, and skin cooling. Nice and easy, nice and short. That's the end of part 1. So I was going to suggest a wee break because I need to go for a pee. Maybe come back in 15 minutes and then we can do the next section on hair. Yeah? Let me say, yeah.
Sounds good.
Yeah.
See you
Yep.
in 15.
15 minutes. So that's a little bit. Well, let's say it's 12, quarter 2. Right? See you all at quarter 2. Actually, do you know what I'll do?